Electricity generating, like every other industry, generates waste wherever fuel is utilized. The waste generated in the process of generating energy must be handled in ways that protect human health while minimize environmental effect. This environmentally beneficial approach, the flow gas desulfurization process, is used to treat waste from power plants, coal, gas, and fuel. The burning of fossil fuels, coal, diesel, food, gasoline, oil, and natural gas for power production, heating, transportation, and industry produces the vast majority of global air pollution. In 2011, fossil fuels represented for 82% of total primary energy supply worldwide.
Oil, natural gas, and coal make for 81% of current fuel usage in the United States. Energy-related fossil fuel conversion in high and middle income countries, as well as biomass burning in low-income countries, are responsible for the majority of global air pollution, accounting for 85% of airborne respirable particulate pollution and nearly all sulfur dioxide and nitrogen oxide emission to the atmosphere. Black carbon, polycyclic aromatic hydrocarbon, PAH, nitrogen and sulfur dioxides, mercury and volatile chemicals that generate ground level ozone are also released. All are associated with multiple adverse health effects in humans. Human health and environmental risks have been connected to sulfur dioxide. The greatest concentrations of this gas are often found around big industrial plants. When breathed, sulfur dioxide can cause a variety of health problems, particularly in the very young, the elderly, and people with respiratory disorder. Sulfur dioxide interacts with other airborne pollutants to produce sulfate, which causes extra respiratory harm, such as tearing lung tissue and damaging the cardiovascular system. Flue gas is gas that exiting to the atmosphere via a flue, which is a pipe or channel for conveying exhaust gases from a fireplace, oven, furnace, boiler, or steam generator. It frequently refers to the combustion exhaust gas produced by power plants. Its composition varies depending on what is burned, although it is normally composed primarily of nitrogen, CO2 and water vapor, as well as excess oxygen, also derived from the combustion air.
It also includes trace amounts of contaminants such as particulate matter, carbon monoxide, nitrogen oxide, and sulfur oxide. A sulfur dioxide is responsible for acid rain formation. Stringent environmental protection regulations have been indicated in many countries to limit the amount of sulfur dioxide. Flue gas desulfurization was an important development to meet environmental challenges. Flue gas desulfurization is commonly FGD is the technology used for removing sulfur dioxide SO2 from the exhaust combustion fuel gases of fossil fuel power plants and from the emission of other sulfur oxide emitting processes. It is a control device that absorbs and reacts using alkaline reagent to produce a solid compound.
The major types of large-scale the power plant FGD system include spray towers, spray dryers, and dry solvent injection system. There are various types of wet scrubbers. For example, spray towers, battery scrubbers, packet towers, and dryer towers. Slurries would cause serious erosion problem in a battery scrubber because of the high speeds at the throat of the battery section. Packet towers or dryer towers would plug up if handling slurries. For handling slurries, the spray tower is good choice and is in fact a commonly used choice in large-scale FGD system. Spray towers use downstream of the particulate equipment electrostatic participator of baghouse. where the flue gas contains very little, if any, combustion fly ash. In a spray tower system, the absorbent slurry is simply injected via spray nozzles into a vertical tower where the slurry droplets are contacted with the upflowing flue gas.
Part of the water in the slurry is evaporated by the hot flue gas, and the flue gas becomes saturated with water vapor. The SO2 dissolves into the slurry droplets and react with the alkaline sorbing particles. The slurry falls to the bottom of the spray tower and is sent to a reaction tank where the reaction is complete and a neutral salt is formed.
Next, for spray dryers, it's used upstream of the particulate removal equipment, electrical precipitator or baghouse, where the fuel gas contains the combustion fly ash. In a spray dryer system, the alkaline sorbate is usually lime slurry. The water is completely evaporated by the hot gas and residence time in the vessel about 10 seconds. Allow the SO2 and any other acid gases such as SO3 and HCI. The dry power is removed from the fuel gas along with the combustion fly ash in the particulate removal equipment. Some of the solid from the particulate removal equipment, fly ash, calcium sulfide, calcium sulfate, and unreacted lime may be recycled and used as part of the sorbent slurry.
Lastly, the dry FGD system simply injects powdered lime or limestone sorbent directly into the flue gas. As shown in the adjacent location diagram, the dry sorbent may be injected into any one of three locations, which is the upper section of the steam generator, the economizer section, the steam generator of the ducting between the air preheater and the electrostatic precipitator. The powdered sorbent is perimeterly injection through lens designed to distribute the sorbent evenly across the flow paths in the flue gas.
When injected into the upper section of the steam generator, it should enter a point where the temperature range is about 900 to 1200 degrees. Injection into the ducting between the preheater and the precipitator should be at point where the flue gas temperature is about 150 to 480 degrees.
When injected into the upper section of the steam generator, it should enter at a point where the temperature range is about 900 to 1200 Celsius. Injection into the economizer should be at a point where the temperature range is about 400 to 600 Celsius. Injection into the ducting between the preheater and the precipitator should be at point where the fuel gas temperature is about 150 to 180 Celsius. Despite the fact that the use of scrubbers reduces air pollution, concerns has been expressed about their possible influence on the marine environment. The uses of scrubbers shift the environmental effect of sulfur from emission to the atmosphere to direct discharge into aquatic systems. The discharge SOx is neutralized by the sweet seawater alkalinity when the washed water from open-loop scrubbers is released back into the sea. The process adds to the continuous ocean acidification caused by an increase in atmospheric CO2 injection into the sea or CS CO2 concentration in the atmosphere rise. The negative impacts of ocean acidification on coral reef and limestone requiring crater have already been detected and are well done.
Furthermore, lowering the pH from roughly 8 to 6.5 causes large volumes of carbon dioxide to be absorbed from the saltwater, contributing to the carbon dioxide emission from the engine exhaust. This partly encouraged the IMO to start the approval procedure to ship-based CO2 collection. Furthermore, in addition to excessive sulfur emission, the scrubbers are known to result in higher emission of other harmful species such as metal and PAHs. Furthermore, the discharge wall has a biochemical oxygen demand, resulting in a decrease in oxygen in the immediate environment and a negative impact on the local marine ecology.
In conclusion, there are technologies other than FGD under development that may offer options for emission control, but they are unlikely to be deployed rapidly enough to obviate the need for FGD in the predictable future. The dominant commercial FGD process is non-regenerable lime or limestone slurry scrubbing.